Hello friends, have you ever run a C++ program and watched it crash without a clear reason? Or noticed it slowly eating up memory until the whole system slowed down? Those problems almost always trace back to one thing: how your program uses memory. In C++, you are directly responsible for memory decisions that other languages hide from you. Get it right, and your programs are fast and reliable. Get it wrong, and you get crashes, leaks, and hard-to-find bugs. Understanding memory allocation is not optional in C++, it is the foundation everything else is built on. In this video, we are going to break it down clearly and simply, starting with the two memory regions your program actually uses. Alright, let us get a clear picture of what we are working with. When your C++ program runs, the operating system gives it two main memory regions to work in. The first is the stack. Think of it like a neat pile of cafeteria trays. Each time you call a function, a new tray gets placed on top. When that function finishes, the tray is removed, clean, and automatic. The second region is the heap, sometimes called the free store. Think of this as a large open warehouse. Space is available, but it is unorganized, and you have to explicitly request it and return it when you are done. Both regions live in your program's memory space, but they behave very differently. Up next, let us zoom in on how the stack actually works when you write local variables in C++. Now look at how the stack actually works. When main starts, the variable a is pushed onto the stack with the value 5. Then add is called with a and 3, so x equals 5, y equals 3, and result equals x plus y, which is 8. Those values all live on the stack. When add returns, its entire frame is popped off automatically, and result is gone. Main then holds b equal to 8. No cleanup code required. Stack allocation is extremely fast, because it is just a pointer moving up and down. The trade-off is size. The stack is small, typically around 1 to 8 megabytes depending on the system, and every variable must have a size known at compile time. Lifetime is also tied to scope. When a function returns, its memory is gone. Next, we will see what happens when automatic lifetime is not enough. Here is the interesting part. When you need memory that outlives a function, or when you do not know the size at compile time, you turn to the heap. You request it with the new keyword, which returns a pointer to the allocated address. So int pointer ptr equals new int of 42 places the value 42 on the heap, and ptr holds that address. You can then modify the value through the pointer, say to 100. Crucially, this memory stays alive until you explicitly release it with delete. After calling delete on ptr, set ptr to null ptr to avoid a dangling pointer, meaning a pointer that still holds an old address after the memory is freed. If you forget delete entirely, that memory is never returned. That is a memory leak. Every new must eventually be matched with a delete. Now let us compare stack and heap directly. Let me show you how stack and heap compare across the factors that matter most. Starting with speed, stack allocation is extremely fast because it is just a pointer adjustment, while heap allocation is slower because the runtime has to find and manage free space. For size, the stack is small, typically 1 to 8 megabytes, while the heap can grow much larger, limited mainly by available RAM. On lifetime, stack variables disappear when their scope ends, but heap memory persists until you explicitly free it with delete. For management, the stack handles itself automatically, while the heap is entirely your responsibility. Finally, the risks. Go too deep with stack frames, for example with uncontrolled recursion, and you hit a stack overflow. Forget a delete on the heap and you get a memory leak that compounds over time. Knowing these trade-offs is exactly how you decide which region to use, which is what we cover next. Alright. Let us put this all together with clear decision rules. Prefer the stack when your data is small, when its size is known at compile time, and when you want the lifetime tied to the current scope. Stack memory is fast, automatic, and safe. Reach for the heap when your data is large, when the size is only known at runtime, or when the object needs to outlive the function that created it. And when you do use the heap, prefer smart pointers like unique pointer or shared pointer instead of raw new and delete. They manage memory automatically and prevent leaks. The key takeaway is this: default to the stack. Use the heap only when you genuinely need its flexibility. That single habit will save you from the most common and painful C++ memory bugs. Thanks for watching, and I will see you in the next one.